Are you able to hear me? For some reason, it looks like I got disconnected. If you can hear me, can you acknowledge in the chat box? Okay. Thank you. Thank you. So far we have seen three, four commands. I want to summarize them so that way you don't. Yeah. So let me. So first command we have seen is see clang minus C minus emit LLVM abs.c. This generates .bc file that is LLVM IR in bitcode format. And now, so we have seen one more command. So it generates .ll file, which generates LLVM IR in a human readable form. So this is one of the primary difference between GCC and LLVM, that is ability to write this intermediate representation on the hard disk and work with it subsequently by running that IR through an optimizer or through a backend component such as LLC or LLI. So, and then, so LLI is the interpreter, LLC is the code generator, and then OPT is the middle end optimizer. Like for example, we can say minus ADCE minus inline maybe, and then we can say, like for example, abs.bc minus O, the optimizer thing we can say in some file. You can say this is an example. So here it is abs.bc, abs.bc. So now we will see a couple of more interesting commands. So one is LLVM assembly. So you can say LLVM AS abs.ll. What it does is it takes human readable form and converts it into bitcode representation. LLVM, it generates abs.bc. If, for example, you remove abs.bc and you do LLVM ASABL, abs.ll, you can see. So this LLVM AS, this is it transforms, generates .bc file from a .ll. And then we have an LLVM disassembler. So like LLVM dis abs.bc, it generates abs.ll. So LLVM from that is, it takes a LLVM bitcode format and generates a human readable intermediate representation. Great. So now what we will do is we will take, we will look at different codes and see how the IR looks like. So let's take this simple code. Add.c. So here we can see, yeah, so it's a very simple program. Let's try to see how this code looks like. And one more thing which I kind of didn't mention here is this for Clang, you can give different options such as O0. Like for example, let's compile Clang abs.c minus s abs.c. We are compiling with minus O1 option. And let's say we store it in abs underscore O1 dot LL. Okay. So if you see, that means we have, when we use minus O1 option, certain optimization options, like for example, if you go see here, certain collection of transformation passes will be applied in a certain order when we use O1 option. Similarly, when we use O2 option, probably a more aggressive collection of optimization or transformation passes will be enabled, and they will be applied in a different order. So let's look at if there is any difference in the code if we compile it using O1 and O2 options. This is O1. View. So this is O2. Yeah, let's not worry about it. Let's see O1. I'm not sure if we can see any difference here in this. Depends on the program. Maybe, yeah. So at this point, it's not clear to me whether O2 is able to do anything better than O1. It's not clear. But let's see how many instructions are there in basic block in O1. 8 to 26. So here also, yeah. In this particular case, O1 and O2, it seems not to make any difference. But let's say if O3 is making any difference. This is a very simple straight line sequence of code. So not much optimization opportunities per se are there, because most of the things that are there, O1 is able to do it. And so it's not like O3 is able to do or O2 is able to do anything special. But let's see what we have here. Yeah, so even in O3 also, in this particular case, this is a small example. And in this example, whatever the optimization opportunities the program is presenting, they are being exploited by using O1 itself. So O2 and O3 are not showing any improvement. But in some cases, or in depending upon the program, so O2 does better than O1 and O3 can do better than O2, etc. Great. So now let's look at, yeah. So this is our program. This is our program. And so let's compile this program using minus O0 option, minus O0. So that is, we are not applying any optimizations. We are not applying any optimizations. So let's do this, and let's look at view control flow graph associated with this. Yeah. Oh, what am I? I'm looking. I think I should be looking at, I should be compiling AD. Let's see. Let's start with the add.c program, and then we move to other programs. So we are compiling add.c with minus O0 option, and we would like to see the control flow graph. As you can see, this control flow graph for this is very simple, because yeah, there is only one basic block in it. And roughly speaking, so we'll try to reverse engineer to the extent possible, to the extent we can figure things out. So this alloc A instruction, in LLVM IR, what it means is allocate memory on the stack. Like for example, here variables A, B, and sum, they are local variables. So they will be allocated memory on the program stack. And actually, if you see this instruction, I don't know why 0 is being stored in this particular location. So this I'm not sure. we will leave it aside. But this instruction is equivalent to assigning the memory location with that is this allocate instruction, it returns an address. So this %2 in LLVM, so the type information is specified, the type of the operand is specified as a part of the instruction. So what it means is, if you look at the store instruction, it has two operands. One operand is a constant 1 and its type is I32. That means it's an integer of size 32 bits, I presume. So you have to check it. So I didn't check it. And %2, its type is, it's a pointer to an integer. So one is stored in a memory location whose address is present in %2. And I think this align 4 means the address should be aligned, because it's essential. The address is for memory locations. If they are not multiples, or if they are not word aligned, then when we go to the machine code level, we get into kind of problems, two kinds of problems. In some machines, that kind of access are not even allowed. Word aligned accesses are not, non-word aligned accesses are not allowed. In some machines they are allowed, but the performance will be bad. This is equivalent to something like A is equal to 1, and this is equivalent to something like B is equal to 4. And so here this A sum is equal to A plus B. It got translated into a sequence of 4 instructions. You go to that memory location, you load it into a register. This is a register. So every variable, if you look at in LLVM IR, it can be something like these variables, they can be allocated memory on the stack, or they will be allocated a register. So %5, it is loaded into a register %5, and it is loaded into, this A is loaded into register 5, B is loaded into register 6, and A, they are added, and the result is stored in a register 7, and we are storing 7 back into a memory location. So this is the memory location where we should be storing is, its address is present in register 4. So if you think about it here, %2 contains the address of A, if I'm right, and %3 contains the address of B, and %4 contains the address of sum, and result is stored back there. And finally, yeah. So this is and then we are loading. We want to return sum, so we are reading sum from that memory location, and we are returning its value. So this is how this whole code is mapped. This whole code is mapped. And one thing here is all the data, it is present in the memory. All the variables, they are allocated memory on the stack, and depending upon the requirement, they are read into some register, and then computations are done and results are stored back to the memory. In the next week's class, when we study code generation, we will talk about this. But this extremely simple code generation could give you pointers on how you can do code gen for your in your compiler. Okay, and yeah. So there is only one basic block. This is how it is. So the compiler, the IR that is generated by the front end, it is always should be in SSA form. So this code is in SSA form because no single register, nothing on the LHS repeat itself. Like %1, it doesn't come again anywhere. %5, it doesn't come on the LHS anywhere. So remember, in static single assignment form, what is there on the LHS, it should occur only once in the code. So This could be in a bad SSA form, but this is in SSA form. So now let's see. We take this, let's clear this. And so what happens is there is an optimization pass or transformation pass called as mem2reg, OPT. What this does is the way when we do minus O0, the way the code gets generated is the code gets generated uh, by using the main memory as the base. But you know, if you just take that code and run, the performance of your code will be extremely bad uh, because it is memory centric. So we want to promote as many memory variables as possible to registers so that the memory traffic will be less. And during this process of promoting these memory variables to registers, this idea of SSA is still be kept. Okay, the program still be in SSA form. The program still be in SSA form. So let's take this code, which is add.ll minus O. We are applying just minus mem2reg to add.ll, and we are storing it in minus m2r.l. This is what we are doing. And then let's look at the so this is so in this particular case, this minus mem2reg optimization module, it is not giving us not much improvement in terms of promoting memory variables to registers. I guess that's what I am seeing. If I am right, let me see. Yeah, so it's not making much difference. It's not making much difference. But one thing we should remember is in order to enable any of the optimization passes subsequently in the LLVM infrastructure, applying mem2reg is important, because if you don't apply mem2reg and try to apply any of the optimization passes, your success will be pretty bad. Not much code transformations will happen. You have to promote the memory variables to registers, and then you should apply other optimizations, because other optimizations kind of assume that this transformation where most of the memory accesses are promoted to registers is done. Now let's take a look at now let's take a look at the second code, add.c. Let's close it. So ABS, yeah. So now look, let's look at this ABS.c. Again, what we do is we compile it using, oh yeah, this is what happened. Okay, so I think let's come back to add.c. Yesterday I figured out something. Let me tell you that. Summary. I forgot. Just give me a minute. Yeah. So it seems when if we don't do this OPT none, then further optimizations will be disabled. So let me try this one. So now what we are doing is we are still working with add.c program. Let's come back here. We are still working with the add.c program. But when we are generating this LLVM IR, we are using this minus disable O0 OPT none, this option. So if we don't do it, grep OPT none add.ll. So it seems this OPT none attribute will be enabled. So because of that, subsequent optimizations on the generated IR will not be enabled. So that we should disable that. So this is yeah. So now let's disable this. This is I did a grep on the previous add.ll which got generated using clang minus emit LLVM. But without this option, so because of that, when we tried to apply mem2reg, nothing interesting happened. Let's hope with this something interesting may happen. So now when I did a grep opt none on add.ll, that attribute is not there. So maybe our this may be better now. Let's see. Yeah, and then let's look at the control flow graph. Yeah, awesome. See, so now with when we did opt mem2reg optimization, so it kind of eliminated everything, and this is all we got. This is the optimized IR. This is optimized IR that we got. In the process of promoting things to registers, etc., it figured memory variables to registers, etc. It figured out a whole bunch of things, and finally, this is the optimized basic block. This is how it looks like. Okay. Thankfully, I remembered it at the right time. Otherwise, we could have come to a wrong conclusion. Now let's look at abs.test. So we have 15 minutes and I want to cover some important ideas before we break for today's class. So let's see how this goes. I hope. Yeah, so now we have abs.c. We are compiling abs.c with minus O0 option. And let's look at OPT. Yeah. So here, this is the control flow graph associated with the ABS program. So if this condition turns out to be true, if this, I don't want to go through the details here, but broadly speaking, so in this basic block, we are comparing, whether, so we are comparing if X is, we are reading printf, printf is executed, scanf is executed, we are comparing if X is greater than 0. So you can see here on this particular line, we are comparing whether X is greater than 0 or not. This is what we are doing here. And here we are loading X into register 6. Here we are loading X into register 6. And I think variable X is allocated memory, and that memory address is present, is allocated memory on the stack, and its address is present in register 2. And here we are checking whether variable 7, the register 7, if it is equal to 0 or not. That is, if it is true or false. If it is true, you go to the true basic block. If it is false, you go to the false basic block. In the true basic block, if X is greater than 0, you don't need to do anything. But if X is less than 0, you have to, you can see, you have to say ABS X is equal to minus X. And that's what we are doing here. Register 12 contains, minus of minus X. And we are storing it in the memory location contained in the register 3. So I think register 3 contains the address of variable ABSX. And then we come here. And if you see here, this code is not, it is in SSA form, but it is not, you don't see any fee function, etc., because everything is handled through memory. So yeah, the optimization opportunities will also be less. But let's say, let's try to apply mem2reg optimization on this and see what happens. abs underscore m2r. Is there anything interesting happening here? Let's see. EBSX. Yeah. Oh, okay, I'm looking at the wrong M2R. Yes. So now you can see earlier we looked at the wrong control flow graph. If you look at the current control flow graph, you can see here in basic block 11, so there is a phi function that says that if you come along this path, you should be taking %7 as the value, and if you are coming along this path, you should be taking %10 as the value. So there is a phi function present here. So when we applied mem2reg, in the process of promoting variables from memory to that are residing on the stack to registers, now the full SSA translation kicks in, and the compiler, the mem2reg module, the component or the pass, transformation pass, ends up inserting phi functions in appropriate basic blocks. All right, I would like you to take a look at this example again later and see how this is all working. Nice. Now let's look at one more code which contains a loop. .c, yeah, sum.c. So here is a program where we read sum and yeah, we read n and we try to compute the sum of first n natural numbers. So here what I do is, instead of doing all this, I'll just directly compile this program, let's say using Llvm option, so that mem2reg is automatically applied on it, and see how the control flow graph looks like. Yes, if you see the control flow graph, so this is before the loop here, there is this, all this thing that is there on line 7, printf on line 7, scanf on line 8, and everything falls in this basic block, and then a condition is checked. Oh, what is this? Am I looking at the correct file? Or it should be a loop, no? What happened to the loop? There should be a loop because the for statement contains a loop, but for some reason it is not showing it. I checked it yesterday at the home, it kind of worked. I just want to see if maybe this optimization is doing something interesting. I don't know. Yeah, so now if you see, when I compiled it using O0, you can see the loop structure clearly. So here you are entering this loop, you keep going like this. At some point when it is false, when the condition is false, you come out of this loop. This is how the for loop got translated. But I don't know what is happening here when I compile it using minus O1 option, UCFG. The loop is gone, so I don't understand what is happening. So you should true, false. Yeah, so not at all clear. Something interesting is happening here, so not sure. But at O0, you can clearly see how the control flow graph is looking. I want you to take a look at this particular program and help me, later after the class is over, tell me what is happening when we are when we compiling with one option. The loop in the control flow graph is in some sense disappearing. So what is happening to it? You should help me out in understanding. Great. So now let's look at this max.c program. So this is the last program we would like to see. So here we are calling a function, and so let's see how it. So minus -0 max dot. Let's close all this. So let's max.c. Yeah, we are compiling it O0 max.c, and let's look at max.ll. So now if you look at this, now you can see there are two control flow graphs, one control flow graph for the main function and another control flow graph for the max. And since we are at O0 level, so the compiler didn't actually did any kind of optimization on this. So there are a lot of memory accesses you can see here. Everything is memory based. So let's say if I compile it using O1 option, let's see what happens. So this is your, when you compile it using O1, compiler does really aggressive. And this whole thing, this select, it does something magic. Yeah, I think I understood what happened before also. But anyway, so let's try to use just OPT minus mem2reg and see what happens. Let's not go all the way. So mem2reg max.ll minus o max underscore m2 output. Yeah, so now also it is, yeah, so now is there, did I enter the right thing? I think now this is the problem. What is that? Demo dot, go to demo. I have to use this option. Otherwise, the compiler wouldn't do anything. Minus O0 minus. Great. OPT. Now it is looking better. Earlier, when we used O1, the compiler is being very aggressive, and it did eliminate many things, and it used some special instruction to do some cool stuff. But anyway, so right now what is happening is, so this is, if you come along this path, then you should use 0, and if you come along this path, you should use 1, where I think register 0 contains variable A, and register 1 contains variable B, and we have a phi function here. So I think you should experiment. So the good thing here is, the important thing here is, when you generate code, you can maybe generate code in a dumb way, in a memory-centric fashion. I'm not sure, you should think about it. So I didn't think about code generation, LLVM IR generation carefully before. and then rely on the rest of the optimization passes to get the job done for you. So now we will kind of take a switch and look at this. There is this nice article which I kind of found online on SSA in LLVM IR. So pay attention here. This as IR is not exact, wouldn't be exactly the same in the LLVM compiler that you will be using, because no, it's a later version of the LLVM compiler, and it could be doing more interesting stuff. The algorithm could be slightly different, things like that. But broadly speaking, but the idea still remains the same. So if A is greater than B, return A, otherwise return B. So here in this entry basic block, we are checking if A is greater than B. If it is true, then we are storing A in return value. Return value is what you would like to return. Return value is a register. And it is allocated memory on the stack using allocate. Maybe use. Okay. And then you go to end. And again, so if you go to false, then you store B in that memory location, and after that you go to end. This is how IR looks like. But if you kind of do mem2reg optimization, then what happens is, so if you go down, so let's see. If you do mem2reg optimization, and this is what we have seen now, so you have a phi function here, and if you come via the true basic block, the ret value register it contains, it will be assigned A, and if you come along the false basic block, then the value that is present in register B is assigned to ret value register. And the parameters A and B, they are residing in the registers A and B. Okay, ret value no longer is allocated memory on the stack, it is promoted to a register. Earlier, using allocate, it is allocated memory on the stack. So now when all this thing is done, and when we map this IR to target machine code, the target machine code, I would like you to keep in mind the backend of the compiler. To the backend of the compiler also, we can mention the level of optimization it can do. Like for example, LLC is a code generator. You can tell LLC to kind of use -O0 to LLC, or -O1 at LLC, or -O2, depending upon which level we use. The backend becomes that level of uses. It becomes that level aggressive in generating and optimizing the backend machine code. So if you take this code and if you use LLC -O0, that is, don't be aggressive, you tell the backend don't be aggressive in your optimization, then remember in the class we have seen that how do we translate code into out of SSA form? How do we translate code into out of SSA form? So if you have something like this, so you say, like x is equal to x1, x is equal to x2, and here this is x3, this is x3. You come like this. So where does this come from? So this comes if we have something like x3 is equal to phi of x1 comma x2. Yeah, my handwriting is a bit bad, but I hope you get the idea. Phi of x1 comma x2. We have a basic block like this. So if we have something like this, when we are translating it out of SSA form, we do this. And you can see something similar here when we are translating this code out of SSA form, because phi doesn't have a realization. So the EDI register contains the variable A, and ESI register contains the variable B. So what we are doing is, in the basic block 1, in the true basic block, we are moving it to this memory location minus, this is a memory location which is there on the stack. And this is associated with the ret val variable. And similarly, in the basic block 2, ESA contains B, and we are moving B into that corresponding memory location, which and finally, we are reading from that memory location and putting it in EAX. EAX contains the return value. That is how the backend convention is. When the return value is returned through a EAX register. In some architectures, especially x86 instruction set architecture. It's a convention. So you can see how this phi function is handled in this code. So where we are moving A, that this is variable A, move variable A into onto the stack. Here we move variable B onto the stack. So that's what, and then here we are moving, let's say this memory location, they correspond to ret value. And this ret value, we are moving it to EAX register. And then we are returning from this function. This is how the translation is happening. But on the contrary, if you kind of tell the compiler, the backend to be aggressive, then what they can, for example, an aggressive backend, it can do, like for example, here in the if part, it is moving. It moves. What it does is, let's see, is this what? Yeah. So instead of moving it to -4 RSP, this stack place, an aggressive compiler can actually move EDI directly into EAX here, and here you can directly move into EAX here, and no, and then finally you don't need this instruction at all. You just return. So if you are aggressive, then you can do this kind of optimization. This is how phi functions are handled in target machine in the backend. So because we have to translate code out of SSA form, and the backend of the compiler does this job by using a variety of strategies. Primary thing is we would like to minimize the main memory traffic, and so yeah, that's what it is. With this, I will conclude today's lecture. And so this is a kind of peek, a preliminary peek into the LLVM compiler infrastructure. So I will see if I can cover any more new ideas in the next class. Otherwise, we will move on to the next idea, that is on runtime environments. So that's all I have for today. If you have any questions, please stay back and ask. Thank you. Have a great day.